Assalamu alaikum. This is lecture number 24 of CS317 Operating Systems. We are starting a new chapter called Deadlocks. We refer to chapter 6 of the William Stallings book on operating systems for this topic. The first subtopic is principles of deadlock. Definitions and conditions. Definition of deadlock. Deadlock can be defined as the permanent blocking of a set of processes that either compete for system resources or communicate with each other. A set of processes is deadlocked when each process in the set is blocked awaiting an event, typically the freeing up of some requested resource that can only be triggered by another blocked process in the set. Deadlock is permanent because none of the events on which the participants of a deadlock are waiting ever happen. Unlike other problems in concurrent process management, there is no efficient solution for deadlock in the general case. A traffic deadlock. Each car wants to move straight ahead. In the figure on the left, deadlock can be avoided if any one of the cars stops where it is. So the figure marked A shows a potential deadlock. Let us suppose that the car marked 2 stops where it is. So the rest of the cars can move, and after they have moved away from the intersection, then the car marked 2 can move straight ahead, and this will not be a deadlock. In the figure on the right, the cars have continued forward until there is no room further. This is a deadlock. Deadlock of processes over resources. Two processes, P and Q, have the general form given in the figure above. P gets A, then gets B, then releases A, then releases B. Q gets B, then gets A, then releases B, then releases A. A joint progress diagram illustrates the progress of two processes competing for two resources A and B. Each process needs exclusive use of both resources for a certain period. In the figure 6.2, the x-axis represents progress in the execution of P and the y-axis represents progress in the execution of Q. For a uniprocessor system, only one process at a time may execute. The path consists of alternating horizontal and vertical segments, with a horizontal segment representing a period when P executes and Q waits, and a vertical segment representing a period when Q executes and P waits. The figure shows 6 different execution paths. Path 1. Q acquires B, then A, and then releases B, and then releases A. When P resumes execution, it will be able to acquire both resources because Q has already finished. Path 2. Q acquires B, then acquires A. P executes and blocks on a request for A because A is with Q. Q releases B and A. When P resumes execution, it acquires both resources. Path 3. Q acquires B, and then P acquires A. Deadlock is inevitable because as execution proceeds, Q will block on A because A is with P, and P will block on B because B is with Q. Execution path 4. P acquires A, and then Q acquires B. Deadlock is inevitable because as execution proceeds, Q will block on A, which is with P, and P will block on B, which is with Q. Path 5. P acquires A and then B. Q executes and blocks on a request for B because B is with P. P releases A and B. When Q resumes execution, it will be able to acquire both resources. Path 6. P acquires A and then B and then releases A and then B. When Q resumes execution, it will be able to acquire both resources because P has already finished execution. The pink shaded area can be referred to as a fatal region. If an execution path enters this fatal region, then deadlock is inevitable. The existence of a fatal region depends on the logic of the two processes. Whether or not deadlock occurs depends on both the dynamics of the execution and on the details of the application. Consider another example. Two processes P and Q have the general form given in the figure above. P gets A, then releases A, then it gets B, then it releases B. Q gets B, then it gets A, then it releases B, then it releases A. If we follow the line marked 1, Q gets B, then gets A, then releases B, then releases A. Now P can execute because Q has finished. If we follow the line marked 2, Q gets B and then gets A, then P starts executing and requests A. P is blocked because A is with Q. Then Q releases B, then it releases A. Now P can get A and execute. If we follow the line marked 3, Q gets B, then P starts executing and gets A, then P releases A. Then Q resumes execution and gets A, then releases B, then releases A. Now P can execute. If we follow the line marked 4, P gets A, then Q starts executing and gets B, then P starts executing and releases A, then Q resumes execution and gets A, then releases B. Now P resumes execution and gets B, then releases B. If we follow the line marked 5, P gets A, then releases A, then gets B. Then Q starts executing and requests B. Q is blocked because B is with P. Then P releases B. Now Q can get B and execute. If we follow the line marked 6, P gets A, then releases A, then gets B, then releases B. Now Q can execute. Regardless of the relative timing of the two processes, deadlock cannot occur. In cases where more than two processes may compete for the same resource, a higher dimensional diagram would be required. Types of resources. Two general categories of resources can be distinguished: reusable resources and consumable resources. Reusable resources. A reusable resource is one that can be safely used by only one process at a time and is not depleted by that use. Processes obtain resource units that they later release for reuse by other processes. Examples of reusable resources include processors, I/O channels, main and secondary memory, devices, and data structures such as files, databases, and semaphores. Deadlock involving reusable resources. Two processes, P and Q, compete for exclusive access to a disk file D and a tape drive T. Deadlock occurs if each process holds one resource and requests the other. If you look at the execution of P, P first requests the disk, then it locks the disk, then it requests the tape, then it locks the tape, then it performs some function, then it unlocks or releases the disk, then it unlocks or releases the tape. If you look at the code for Q, Q first requests the tape, then it locks the tape for itself, then it requests the disk, then it locks the disk for itself, then it performs some function, then it unlocks the tape, then it unlocks the disk. Deadlock occurs if the multi-programming system interleaves the execution of the two processes as follows: P0 P1, Q0 Q1, P2 Q2. So deadlock will occur if P requests the disks, gets the disk and locks it for itself, then Q requests the tape, gets the tape and locks it for itself, and then P requests the tape and Q requests the disk. None of the second requests of both the processes can be granted, and this is a deadlock. Deadlock involving main memory. Suppose the space available for allocation is 200 kilobytes. The sequence of requests that occurs is depicted in the picture. So we have two processes, P1 and P2. P1 makes an initial request of 80 kilobytes. Later it asks for 60 kilobytes more. P2 makes an initial request of 70 kilobytes and later somewhere in its code it asks again for 80 kilobytes. Deadlock occurs if both processes progress to their second request. So if we give 80 kilobytes to P1 and 70 kilobytes to P2, we are only left with 50 kilobytes now. Now we cannot satisfy the 60 kilobyte request of P1. We can also not satisfy the 80 kilobytes request of P2. This is a deadlock. The best way to deal with this problem is by using virtual memory. Consumable resources. A consumable resource is one that can be created, produced, and destroyed, consumed. Typically, there is no limit on the number of consumable resources of a type. An unblocked producing process, called a producer, may create any number of such resources. When a resource is acquired by a consuming process, the resource ceases to exist because the consumer eats it up. Examples of consumable resources are interrupts, signals, messages, and information in I/O buffers. Deadlock involving consumable resources. Consider the pair of processes shown in the figure, in which each process attempts to receive a message from the other process and then send a message to the other process. Deadlock occurs if the receive is blocking, that is, the receiving process is blocked until the message is received. Resource allocation graphs. A useful tool in characterizing the allocation of resources to processes is the resource allocation graph. The resource allocation graph is a directed graph that depicts a state of the system of resources and processes, with each process and each resource represented by a node. Within a resource node, a dot is shown for each instance of that resource. Examples of resource types that may have multiple instances are I/O devices that are allocated by a resource management module in the operating system. Continuing with resource allocation graphs, a graph edge directed from a process to a resource indicates a resource that has been requested by the process but not yet granted. A graph edge directed from a reusable resource node dot to a process indicates a request that has been granted. That is, the process has been assigned one unit of that resource. A graph edge directed from a consumable resource node dot to a process indicates that the process is the producer of that resource. A resource allocation graph with deadlock. There is only one unit each of resources RA and RB. P1 requests RA. RA's single instance is held by P2. P2 requests RB. RB's only instance is held by P1. So P1 holds RB and requests RA, while P2 holds RA but requests RB, and this is a deadlock. A resource allocation graph without deadlock. P1 requests RA. There are three instances of RA. One of them is held by P2. P2 requests an instance of RB. Two instances of RB are there. One is held by P1. There are 3 units of RA and 2 units of RB. P1 holds RB and requests RA, while P2 holds RA and requests RB. No deadlock, as multiple instances of resources are available. Again, we see a resource allocation graph with deadlock. RA is held by P1, which is requesting RB. RB is held by P2, which wants RC. RC is held by P3, which wants RD. RD is held by P4, which wants RA. Note that in this case, we do not have a simple situation in which two processes each have one resource the other needs. Rather, in this case, there is a circular chain of processes and resources that results in deadlock. The conditions for deadlock. Three conditions of policy must be present for a deadlock to be possible. Mutual exclusion. Only one process may use a resource at a time. No process may access a resource unit that has been allocated to another process. What does this mean? This means that a resource on which we have enforced mutual exclusion can lead to a deadlock. But a resource on which we have not enforced mutual exclusion will never lead to a deadlock. And if you go back to the concurrency chapter, I told you that mutual exclusion is enforced over resources that are shared and modifiable. Hold and wait. A process may hold allocated resources while awaiting assignment of other resources. So, suppose that a process asks for 3 resources, 2 of them are free right now. So, the operating system gives the process these 2 free resources. Now, the process is waiting for the third resource. This is the condition of hold and wait. If nobody is holding and simultaneously waiting in your system, deadlock cannot occur. Deadlock will only occur in a system where people are holding some resources and waiting for some resources. No preemption. No resource can be forcibly removed from a process holding it. If I give a resource to a process and I can forcibly take it away at any time, deadlock can never occur due to this resource. But sometimes there are resources that I grant and I cannot forcibly take them away. Only the process will relinquish it after it has done its work with the resource. In such resources, deadlock can arise. The first 3 conditions are necessary but not sufficient for a deadlock to exist. For deadlock to take place, we require a fourth condition, circular wait. A closed chain of processes exists such that each process holds at least one resource needed by the next process in the chain. So P1 needs the resource held by P2, which needs the resource held by P3, which needs the resource held by P4, and finally the last process in the chain needs a resource held by P1, the first process of the chain. This completes a circle. This condition needs to be present for us to say, yes, this is a deadlock. Necessary and sufficient conditions for deadlock. If you look at the picture over here, if in a system we have the condition of mutual exclusion, the condition of no preemption, and the condition of hold and wait, there is a possibility of deadlock. But if in the system all 4 conditions are present, mutual exclusion, no preemption, hold and wait, and circular wait, this leads to a sure shot existence of deadlock. The fourth condition is a potential consequence of the first 3. That is, given that the first 3 conditions exist, a sequence of events may occur that lead to an unresolvable circular wait. The unresolvable circular wait is in fact the definition of deadlock. The circular wait is unresolvable because the first 3 conditions hold. I cannot have 2 people access the same resource at the same time. Why? Because I have enforced mutual exclusion. I cannot take away a resource that I have already allocated. Why? Because I have no preemption. And in the deadlock, there are processes which already have some resources and are additionally waiting for some resources. So all the first 3 conditions hold. The 4 conditions constitute necessary and sufficient conditions for deadlock. Pause the video, write your answer in a Word file and save it as my roll number underscore lecture 24. Task 1 says, what is a necessary condition? Task 2 says, what is a sufficient condition? Let me give you a hint. In discrete structures, you read about implication. Both of these questions and both of these conditions have got something to do with the logical implication. Find out. Approaches for dealing with deadlock. Many researchers have given different ways of dealing with deadlock. Three general approaches exist for dealing with deadlock. Number one can prevent deadlock by adopting a policy that eliminates one of the four conditions. We have already seen that deadlock occurs when mutual exclusion, no preemption, hold and wait, and circular wait. All these conditions are true in the system. Then deadlock occurs. So why don't you and I sit together and design a system in which one of these four conditions is always false? If we keep one of these four conditions always false, deadlock cannot occur in our system. Easy? This is called deadlock prevention. One can avoid deadlock by making the appropriate dynamic choices based on the current state of resource allocation. Okay, so what happens is that I am the operating system and I have many resources which I am constantly allocating to the processes, and when they're done with them, they bring the resources back to me. So I have a pool of total resources. What if I develop a bit of intelligence and whenever I am allocating resources, I check my pool and figure out if allocating this number of resources to this person is a good idea or a bad idea. Will I run out of resources that I can allocate? And if so, then I should probably not uh, grant this request. So this is known as deadlock avoidance. Looking at the state of the system, looking at the resources that I have free, looking at the resources that I have already allocated to people, and then looking at a request and figuring out if this request is going to take me to a deadlock or not. The deadlock prevention strategy is enforced at design time of the operating system. When the operating system is being designed, you take steps to nullify one of the four conditions of deadlock. The deadlock avoidance strategy is carried out throughout the running of the operating system, as long as the operating system runs. The third strategy is one can attempt to detect the presence of deadlock and take action to recover. So the third strategy is a laid back strategy. I say let hell break loose, let deadlock come. And when deadlock will come, then I will first detect or identify that yes, this is a deadlock, and then I will try to recover from that deadlock. But if deadlock is not arising, I am not going to do anything with it. I will only take steps when the system is indeed deadlocked. So these are three approaches that we can use with deadlocks: deadlock prevention, deadlock avoidance, deadlock detection, and recovery. And we'll talk about them one by one. Now let us talk about deadlock prevention. As I have already explained to you, deadlock prevention takes place at the design time of the operating system, where you create a policy such that one of the four conditions of deadlock is always false in your system. Let me remind you that the four conditions were mutual exclusion, no preemption, hold and wait, and circular wait. So you construct a policy such that one of these conditions is nullified. And in this way, deadlock can never occur in your system. Methods of deadlock prevention. The strategy of deadlock prevention is to design a system in such a way that the possibility of deadlock is excluded. We can view deadlock prevention methods as falling into two classes. An indirect method of deadlock prevention is to prevent the occurrence of one of the three necessary conditions listed previously: mutual exclusion, hold and wait, no preemption. A direct method of deadlock prevention is to prevent the occurrence of a circular wait. Nullifying mutual exclusion. In general, the first of the four listed conditions cannot be nullified. If access to a resource requires mutual exclusion, then mutual exclusion must be supported by the operating system. Some resources, such as files, may allow multiple accesses for reads, but only exclusive access for writes. Even in this case, deadlock can occur if more than one process requires write permission. We have seen the producer-consumer problem. There was a shared buffer there, and the producers were putting data into it, and the consumers were taking data from it. And just consider for a moment that you have no mutual exclusion over that shared buffer. Then there is no guarantee, whatever code you write, that it will actually implement the producer consumer problem. The other problem that we saw was the readers writers problem. And we were implementing mutual exclusion for the writers. Consider that we don't implement mutual exclusion. Then two readers or two writers can come in. Now, two readers come in, fine. We have no problem with that. But two writers come in at the same time and they try to write a file. What would be the final condition of the file? No idea. I have no idea. So the thing is that mutual exclusion is something that we require for the correct function of the system. And nullifying it will lead to a system which will not function as we want it to function. That is why we never nullify the first condition of deadlock, which is mutual exclusion. Nullifying hold and wait. The hold and wait condition can be prevented by requiring that a process request all its required resources at one time and blocking the process until all requests can be granted simultaneously. Suppose that a process requires 5 resources. So the process must declare at the start of execution that it requires these 5 resources. And then it must wait till we give it all the 5 resources. We are actually nullifying hold here and we are making the process wait. So if you are asking for 5 resources and I don't have all 5 of them for you free, I am not going to give you any and I am going to make you wait. So you will be waiting, holding nothing. This is the procedure. This is the policy that we adopt. This approach is inefficient in two ways. A process may be held up for a long time, waiting for all its resource requests to be filled, when in fact it could have started execution with only some of the resources. See, it could be that the process needed only two resources in the first 100 lines of code, and it needed the other three resources in the last 100 lines of code. And the total lines of code are, let us say, 600. So the process could have gotten the resources for the first 100 lines of code and merrily made its way to the last 100 lines of code where it would have asked us again for the remaining three resources. So the process could have worked with a lesser number of resources, but it is waiting. Resources allocated to a process may remain unused for a considerable period, during which time they are denied to other processes. This is because the process uses a resource in only some of its total lines of code. I just gave you an example that the process uses two resources in the first 100 lines and three resources in the last 100 lines. So actually it needs the resources in 200 lines, but it is going to keep those resources with itself for all its code. And during that time, when somebody else requests for those resources, the operating system will turn that somebody else down. Another problem is that a process may not know in advance all the resources that it will require. This is a big problem. A process may not know what resources it requires because processes are composed of if and else structures. So there might be code like if x is this value, then demand resource A. If x is this value, then demand resource B. How is the process going to know the value of x at runtime when it has not begun running yet? So this is a problem. There is also the practical problem created by the use of modular programming or a multi-threaded structure for an application. An application would need to be aware of all resources that will be requested at all levels or in all modules to make the simultaneous request. But in modular or multi-threaded programming, this information may be difficult to get by because you may be using functions written by somebody else. You may be using functions from a library that you have not created yourself. Nullifying no preemption. These protocols are practical only when applied to resources whose state can be easily saved and restored later, as in the case with a processor. So if you cannot save and restore the state of a resource, you cannot preempt it. No preemption condition can be prevented in several ways. 1. If a process holding certain resources is denied a further request, that process must release its original resources and, if necessary, request them again together with the additional resource. A process asks for resource A, it's free, it is granted. It asks for resource B, it's free, so it is granted. It asks for resource C, but resource C is not free, so this process has to relinquish resource A and resource B. Now, if it only needs resource C, it will make the request for resource C only. If it needs all three of them, it will make a request for all three of them again. 2. If a process requests a resource that is currently held by another process, the OS may preempt the second process and require it to release its resources. This scheme would prevent deadlock only if the two processes do not possess the same priority. So you cannot use this scheme when both the processes have the same priority. And the scheme is like this. The resource is currently with a process. This is the first process. Another process requests the resource. This is the second process. When the OS sees that it cannot give the resource to the second process, it preempts the second process and takes all the resources that it gave the second process back. Nullifying circular wait. The circular wait condition can be prevented by defining a linear ordering of resource types. We allocate an index with each resource type. If a process has been allocated resource Ri, then it may subsequently request Rx such that x is greater than I. Resource Ri precedes Rj in the ordering as I is less than j. Suppose that a process A has acquired Ri and a process B has acquired Rj. A requests Rj and is blocked. A can make this request because it has Ri and wants Rj. B wants to request Ri, but B cannot make this request because it has Rj. It cannot ask for a resource prior to J. It can only ask for resources successive to J. So B will have to relinquish Rj. A can now be served. As with hold and wait prevention, circular wait prevention may be inefficient, slowing down processes and denying resource access unnecessarily. Lessons from the lecture. We understood what a deadlock is. We realized that there are two types of resources in a computer system. We explored the conditions for deadlock. We listed the approaches to deal with deadlock, and we explored deadlock prevention. Things to do: read the book, find the answers to the tasks, note your questions on a piece of paper, and email your suggestions to me. Take care. Allah Hafiz.